Hey everyone, today we're diving into what I consider a quiet yet absolutely profound milestone in the world of computing. We're going to explore the incredible story of the day, a simple specification document, guided an AI to build hardware completely from scratch. If you've been thinking of AI as just a handy little coding assistant, well, prepare to have your mind blown. We are about to look at the exact moment AI stepped up to become a fully autonomous engineer. The human architect behind this project actually summed it up perfectly. They said, perhaps somewhat exaggerated to say so, but I feel this may have been a small turning point in computing. And honestly, I don't think that's an exaggeration at all. What we are looking at here isn't just about auto-generating some neat code. It is a fundamental, ground-up shift in how we might design hardware moving forward. So, here's the big, central question we need to keep in mind today. Can a single-sentence prompt, paired with a well-written specification document, actually guide an AI to autonomously engineer a working processor? It sounds a bit like sci-fi, right? But the answer to this question sets up the entire journey we're about to go on, showing exactly how the development process is evolving right before our eyes. All right, let's jump straight into our first piece of the puzzle, the precaution behind the specification. This whole story actually kicks off with the human architect in a bit of a panic. Let's look at the timeline for this open source processor, known as PTSG Core. The human architect was rushing in a complete frenzy to draft chapters 4 and 5 of the spec on May 25th and 26th. And then, just days later, by May 30th, the entire AI implementation was finished. We are literally contrasting days of frantic human planning with just hours of AI execution. But why was the human scrambling so much in the first place? Well, the architect realized something kind of wild. They noted, the reason I rushed chapters 4 and 5 was that I was worried the content would be made from only the information up to chapter 3. Basically, during early tests, AI models were already accurately predicting the chapters that hadn't even been written yet. The human had to scramble to establish a single official truth before the AI just went ahead and confidently made up its own specs. This brings us to a really fascinating concept called latent forking. It's a scenario where multiple AI readers try to guess unwritten specifications, and their implementations just diverge wildly out of control. So you see, this specification wasn't written just to explain things to the AI. It was written as a strict guardrail. It was a precaution to close that inference gap and give the AI a single, rock-solid target to aim for. Okay, moving right along to the inciting incident. And honestly, what triggered the AI was shockingly brief. Once that 5-chapter spec was locked in, what was the magic instruction that kicked everything off? Literally just this. Read this repository and code the top layer of PTSG Core's Verilog source. That's it. There's no architectural hand-holding, no warnings about tricky bugs to watch out for. Just a pure, incredibly simple command to act on the specification. Which brings us to the really exciting part, the AI taking over and showing off its autonomous engineering chops. Let's step into the shoes of the AI agent, Claude Code, in this case. This wasn't just a simple one-shot text generation trick. The AI thoroughly read all 5 chapters, wrote and compiled the Verilog code, wrote the test benches, debugged its own errors, and even critically evaluated external code reviews. We're talking about a sustained, fully autonomous engineering loop that went on for hours. It was acting like a real, dedicated developer. And check out this log from the AI. It says, the loop test exposed a real issue. My base set autosaves every time, triggering an unacknowledged stack push and hanging. I mean, doesn't that sound exactly like an experienced human engineer muttering to themselves as they find a bug in their own work? It realized it accidentally created an infinite loop, diagnosed the core memory issue, and just got straight to work fixing it. The engineering discipline gets even better. When an external automated review from Gemini flagged 2 potential issues, Claude Code didn't just blindly accept the changes. It literally said, let me evaluate both against the spec and my code, rather than apply blindly. It treated the external review as an opinion to be questioned, while treating the human-written specification as the ultimate law. That is a brilliant display of true engineering ethics. And then, the AI takes full accountability for messing up. It confesses, there's a real test failure I pushed prematurely. I should not have committed with a failing test. Let me debug it immediately. Taking responsibility for a broken test like this, I'd say that proves it passes a Turing test, not just for sounding conversational, but for having actual, rock-solid engineering integrity. Now, we reach the climax of the story.
Discovering ambiguity in the spec, where the AI had to step up when the humans dropped the ball.
Here's where things get super interesting. The AI ran into a massive blind spot that the human architects completely missed. The specification was totally silent on how the autosave should work during a loop. Does it save on every single loop iteration, or only when the base address actually changes? The human instructions literally had a huge hole in them. Faced with this missing info, the AI evaluated 3 possible routes: an idempotent route where it only saves when changed, an always push route, or a conditional route. And it made a highly defensible engineering call, choosing the idempotent route, which is by far the safest option. But crucially, it didn't just quietly patch it. It documented this tie for human evaluation later. It autonomously resolved the ambiguity while perfectly closing the feedback loop to improve the original spec. Let's zoom out for a second and look at the 3 tiers of verification that made this whole project work. This whole endeavor was essentially a massive working hypothesis tested across 3 tiers. First, comprehension. Can the spec be understood? Gemini proved yes. Second, deliberation. Can the spec be reasoned over to find bugs? Gemini proved yes again. Finally, implementation. Can it actually be built? And Claude Code proved that it absolutely could. Off-the-shelf AI models successfully handled every single one of these tiers. So, what does this quiet little milestone mean for the future of computer design? Well, the architect believes AI coding agents are unlocking 3 radical new capabilities. First, the autonomous formation of specifications. Second, which we just saw, specification-driven hardware generation. And third, behavior-to-hardware inversion. Let's talk about that inverted flow for a second, because it's a real game changer. Traditionally, you design a processor, and then you write programs to run on it. But in an inverted flow, you write a program that expresses the behavior you want, and then the AI derives the minimum processor configuration needed to run it. The processor is literally born from the program. It's a complete flip of the traditional design process. The project logs sum this up so beautifully. They read, "The path from words to working hardware was walked by something that was not a person, and the words were written so that this would be possible." It is just awe-inspiring to think about. On that single quiet day in May, a specification directly guided an AI to create working hardware. So I'll leave you with this thought. Are we standing at the turning point where we no longer write programs for processors, but custom processors are born directly from our programs? The future of how we build computers is completely transforming, and I, for one, can't wait to see where it goes next. Thanks so much for joining me today to explore this amazing shift.